In today's lesson, we will be learning about variables and expressions. This is the first lesson from Chapter 2, and our goal today will be to evaluate expressions. Please make sure that at this time you're following along with your note skeleton sheet, and make sure you pause the video as needed so that you're able to fill in and complete the sheet as we go through the video today. In order to be successful today, there's some key vocabulary that we need to go over. Make sure that as we go over this vocabulary, you're filling in the blanks on your note skeleton. The first term that's important to us is numerical expressions, which are mathematical phrases with only numbers and operation symbols. Really important for us to note that only numbers and operation symbols are present in numerical expressions. Some key examples that we could write down of numerical expressions on is going to be anything that involves a string of numbers connected with operation symbols. So we could have something like 4 plus 8. We could have something like 9 divided by 2. We could have something like 16 minus 8 plus 4 times 6. So all of those examples of order of operations problems that we practiced in the last chapter, each of those would be examples of numerical expressions. They were different combinations of numbers connected with operation symbols. Oftentimes we work with whole numbers, but it's important to note that we could have either fractions or decimals involved in our numerical expressions as well. So something like 0.5 plus 8.25 would be a numerical expression, and 1/2 minus 3/16 would also be a numerical expression. As long as we have numbers and operation symbols, and those are the only two things present, we have a numerical expression. The reason the idea that numerical expressions only involved numbers and operations is important as we start to take a look at variables and constants, which are our next two definitions. Variables are letters that represent an unknown number. So we've seen this before in past textbooks or lessons or over the last couple years in math class, but we might see an X or an N or a Y. Any of the 26 letters in the alphabet is available to us to use as a variable. We place that when we don't know what a number is or need to represent a number that could represent lots of different numbers. A constant, and the opposite, however, is a quantity that does not change. It's a value of a number that's going to stay the same no matter what. So the fact that there are 12 inches in a foot, that's a constant. That thing is going to change. In the expressions before, when we had 4 plus 8, 4 doesn't change itself. We can't make that into a new value until we add 8 to it. So any single number in a problem, like 4 or 12 or 186 or 1/3 or 4.5, all of those would be constants as their value is not going to change. In expressions that have variables, which we're going to get to in just a minute, the letter could represent multiple different numbers, but the constants or the single numbers that are given to us are never going to change. In the box provided on your note skeleton that compares variables and constants, let's take a look at a couple examples. Make sure that you fill these in on your chart. The first example says the number of horses on a farm. If I'm debating whether this is a variable or a constant, I need to think about the key difference between these two terms. The key difference is a constant does not change, where a variable could represent any number. I know that on a farm, a lot of things could happen to the number of horses. A farmer could buy more horses and therefore increase their total. A farmer could sell their horses and decrease their total. Horses could have babies, and those babies could increase the total, or a horse could die, which could change and decrease the number of horses on that farm. So based on all of those scenarios, the number of horses on a farm would have to be a variable. That's a number that could change depending on a number of different circumstances. If I look at the next example, the number of months in a year, I know that this year has 12 months, January to December. I know last year had those same 12 months, and next year we'll have 12 months as well. So that number doesn't change. Each year there are going to be 12 months in a year. So I'm going to place number of months in a year under the title constants. At this point, I'd like you to pause your video. I'd like you to carefully think about each of the 4 examples below, placing them where you think they would go, either as a variable or a constant, using the same type of strategy and thinking that I just used for the first 2 examples. After you finish going through those 4 examples, I'd like you to start the video and you can check to see whether your answers are right. Good luck! If you have already taken a look at these 4 examples, you should be able to check your work now as I go along through them. So if I'm looking at the number of ounces in a pound, I know that there are 16 ounces in a pound. Even if I wasn't sure of that exact value, I should be aware that there's a particular number of ounces in a pound, and that value is not going to change based on what I want or I think. That value is going to stay the same, so it's going to be a constant. If I look at the number of members on a team, like a soccer team, I can think about my soccer team at Holy Ghost. I know that some days our entire team is present at school, so we have a full 24, I think that is on JV. Sometimes, though, a student is sick or going out of town, and that decreases the number of members we have on the team. At other times, we could gain a student, whether someone decides that they want to play or someone becomes academically eligible or a new student comes to school, we could add on members as well. So that number can change. So I'm going to place that under the variables column. If I look at the number of students in a class, the same logic I was describing for the members of a team applies. I could have students enter the school, people could move to our neighborhood and want to join, students might leave the school, students might be sick and might not be present on a particular day, so that the number of students in a class could change and is therefore going to be a variable. If I look at the number of grams in a kilogram, I know that there are 1,000 grams in each kilogram. That number is going to stay the same no matter what, so I'm going to place that under the constant category. Make sure that if you had any of these incorrectly placed on your note skeleton, that you're erasing and putting them in the correct spot. We'll get to more practice with this in class, but we want to make sure that you have good notes that you can refer back to that have the correct answers. The next important vocabulary term for us to go over is the algebraic expression, which kind of combines the numerical expression with the idea of variables that we've just talked about. An algebraic expression is a mathematical phrase that contains one or more variables in addition to the numbers and operation symbols. So some examples you might include of algebraic expressions would be 3 plus y, or m plus 8, or x minus 2. 3y we know is an expression as well. Even though we do not see an operation between those two, we know that when a number and a variable, or 2 variables, are right next to each other, the missing operation is actually multiplication. So 3y would mean the same thing as 3 times y. We could also see x, y, z, 3 letters right next to each other, 3 variables that could represent different numbers, and that just indicates for us that we should multiply x times y times z. An expression could be even longer than any of these examples and could contain a string of letters, variables, and numbers, similar to the way we saw with a numerical expression. So something like 3x plus y minus 8 times 4 plus 2. Notice that I put a time symbol like an x. If I'm looking at this, it's really difficult for me to distinguish between the variable x next to the 3 and that multiplication symbol. So when we do algebra, we do not use an x anymore to represent multiplication. That's where that idea of the 2 numbers right next to each other, the 3y, comes from, and why we don't see the multiplication symbol between them. However, if you're not writing the letter and the variable next to each other, say if we're multiplying 2 numbers, like 8 times 4, we can't put the 8 and 4 right next to each other, or it will look like the number 84. But what we can do is draw a dot, and that dot is our new multiplication symbol when we work with algebra. Our last vocabulary word for today is what's going to help us actually know what it means to evaluate an expression, which was the goal of our lesson today, and that simply means to replace each variable with a number. Then you use the order of operations to simplify the expression. If you notice in example number 1, it says evaluate 2x minus 8 for x equals 11. In order for us to evaluate this expression, I'm going to replace that letter x, that variable, with the number 11. Notice when I go to copy down my expression, which should be my first step, if I put 2 and I put that 11 in for x right next to each other, that looks like the number 211. Again, I want to place my dot to show that I'm multiplying because 2 right next to x indicated that we should have multiplication, and then I still need to write down my minus 8. Notice in my definition, I need to use the order of operations. Since I remember that in PEMDAS, multiplication comes before subtraction, I'm going to do 2 times 11 first, and then just like I did with order of operations, I'm going to copy down what I've replaced 2 times 11 to equal 22. I still haven't used my minus 8 yet, so I'm going to bring that down to the line, then I'm going to do 22 minus 8, which I know to be 14, and 14 is going to be my final answer. At this point, we're going to try example number 2. If you feel confident about evaluating expressions, I challenge you to pause the video and try it yourself before we go over the video together. If not, though, hold on and we'll go over this example together and you can give example 3 a try by yourself. So when I want to evaluate this expression, I want to copy down whatever I have, so 56 minus 4, except instead of the x, this time I'm replacing it with a 7. Again, I can't just put the 7 right next to it, or it looks like 56 minus 47. I need to remember that 4 next to the x indicates I should multiply 4 times whatever x is. So since x is 7, I'm going to multiply the 4 by 7. I'm going to do that first because, again, order of operations tells me I should do multiplication before my subtraction. So I'm simply going to copy down my 56 minus. Instead of 4 times 7, however, I'm going to replace that with a 28. I'm going to simplify. At this point, all I have is subtraction left, so I'm going to subtract 56 minus 28, which is going to give me 28, and 28 is going to be my final answer. At this point, I'd like you to pause the video, if you haven't done so already for the first example, and I want you to try example number 3 on your note skeleton, and then return back to the video to check and see whether or not you did your answer correctly. If you did not, if you made a mistake, please fix it on your note skeleton sheet so that, again, you have the correct notes to go back and refer to. So if you've done that, you should, and you've restarted your video, you can catch up with me now as we go over the answers to the problem. So again, I'm going to copy the problem as I have it given, 78 minus 4, except instead of that m, I'm going to put the number 5. Again, since it's not 45, but 4 times 5, I'm going to put my dot in between, and I'm going to add 6 to that. Going with the order of operations, I'm going to copy down my 78 and my minus symbol, but instead of 4 times 5, I'm going to replace that with 20, which is the simplified form, and I'm going to add 6 to that. At this point, I only have subtraction and addition left, so I remember that if I only have those two operations, I work from left to right. So subtraction is going to come first. I'm going to do 78 minus 20 and get 58. And I'm still going to have to add 6 to my answer. And when I do that, I'm going to get 64, which is going to be the evaluation of 78 minus 4m plus 6 when m equals 5. For my last example, we're going to see how this might work in a word problem. So the problem given to us was you earn $3 for each person who plays the game at your booth at the school fair. The expression 3p represents the amount of money you earn, where p is the number of people who play your game. Find the amount of money you would earn if 15 people came to your booth, if 40 people did, or if 65 people did. So what you see on your screen is a chart that might help us organize the information that we're setting up for this. We're looking at the amount of people, which is represented by the variable p, because we know that that value can change. So I'm going to put that under number of people. The process, or how I'm going to find out how much I earn, is I'm going to do 3, because I earn $3 for each person, times the number of people that play. And then my amount earned for p people would just be 3p, or 3 times p dollars. Always want to remember my unit sign. However, the question asked me for a couple different values. They wanted to know if I get 15 people, what will happen? If I get 40 people, what will happen? And if I get 65 people, what will happen? So in essence, I'm using that same expression for 3 different values this time. So if I replace my p, my number of people, with 15, I'm going to do 15 times 3 for those $3 for each person to figure out that I would earn $45. If I had 40 people attend my booth, I would do 3 times 40, or $120. And if I had 65 people, I would still use that same process of 3, but this time I'm multiplying it by 65, so I'd get $195 if I had that many people stop at my booth. Sometimes an expression might have 2 different variables. In that case, I just have to be careful about what variables I'm given and make sure that I substitute the right variable into the right part of the expression. So for this example, it tells me that the expression 2L plus W plus 2W gives the distance around a rectangle with a length L and a width W. We want to find the distance around a rectangle with the length 7 centimeters and the width 4 centimeters. So I'm going to start out by writing my expression. Instead of L, though, I'm going to look back to my example. It tells me that the length is 7 centimeters. So instead of L, I'm going to put a 7. Then I have an addition symbol and a 2. Instead of W, I notice that the width is 4 centimeters. So I'm going to replace that with a 4 and put my multiplication symbol between the 2. Now to use the order of operations, I know I have to do multiplication first. So I'm going to do 2 times 7 is 14. Still haven't used my plus, my 2, and I have another multiplication. So I'm going to do that next. So 2 times 4 is 8. I'm going to add the other pieces I still haven't used, and I'm going to get 22 when I add 14 plus 8. So I have 22. Now I need to go back. This is a word problem. I need to think about what my units would be. I'm looking at the distance around a rectangle. So distance is going to be some sort of distance measurement. This particular problem talked about centimeters. So I will have 22 centimeters as my answer and the distance around a rectangle. At this point, you can go back and review any parts of the video that you feel would be helpful to help you go over the 4 example problems that are found at the bottom of your notes skeleton. And we will go over these when I see you in class tomorrow. Enjoy and have a good evening.